and I hope you're ready because we're going to get heavy now. So I imagine that since you are here to play with me, it's because you're also interested in supermassive black hole. So I want to invite you to an adventure closer to these very intriguing objects. So to start our adventure, we have to know where we are, so we know where to go, right? So this is an example of how we think our galaxy is, the Milky Way, and this is where we are located in our humble planet Earth. And the supermassive black hole that is closer to us is the one that's lying in the center of our galaxy, and it's called Sagittarius A star. So what I'm going to propose us to do today is to make a journey in which we go close to the central supermassive black hole to understand a bit more what do we have there and what do we understand so far about black holes. And then we're going to come back to be safely here on Earth without any dangers of being swallowed by the black hole and not coming back again. And then I'm going to tell you a bit of what can we do to understand these objects when we are here in the planet. Okay, so let's start our journey by getting close to the center of our galaxy. So we're going in the direction of the constellation of Sagittarius, where our black hole is. But then, if we are looking for a black hole, how are we going to know where we find them? If the thing is not shining, if it's black, how do we know that we reach the center where we want to study? Well, we have been going through many stars, gas, and dust. All these objects will be shining. And then to understand when we get close to our black hole, we want to see how these shining objects are interacting with this very massive object that will have a very strong gravitational field. And that is actually what some scientists did in 2020. They managed to have a Nobel Prize in Physics by studying the motion of the stars in the center of the galaxy. So if you pay attention to this star here, you see that it makes a movement as if it was orbiting something, but there is not actually something bright there. So that could be an indication of the dark object that we are looking for. So this is one of the observations that led to the Nobel Prize, in which they are seeing the dance of the stars around this point in which we could not see anything. But just by measuring these movements, we could estimate the mass of this object. And it's over 1 million times the mass of our star, the Sun. So, okay, we found a supermassive black object. But what are we talking about? Well, this is a simulation of a black hole, so this is what we expect to see if we find one. And we see here, this is black sphere. This is the black hole itself. And we see that there is an accretion disk, this disk of brown matter around it. So accretion means that the black hole is slowly swallowing matter or capturing matter inside it. And this matter, before falling inside the black hole, will be shaped like this in a disk. And we also see these shapes on the top and on the bottom. And this is actually just an optical effect of the light. So the gravitational field of this object is so strong that the light from the accretion disk behind the black hole is being bended toward us. And that's why we see something like this. And now, let's get back to our supermassive black hole, since we are in the journey to understand Sagittarius A star a bit more. And this is what we see when we look at it. This image got a bit famous. We needed some telescopes all over the planet to simulate a telescope that would have a mirror of the size of planet Earth, so we can take a picture like this of our black hole. But we still don't really understand everything that is going on here. For example, these blobs here, we don't understand if they are, for example, this accretion disk that I was showing you, or if it's just the same blob that is going around in a long disposition picture that we have to take. So, let's understand a bit better, like black holes, what am I talking about? Well, first let's understand how a normal object is like. So this could be me, you, a pen, or whatever. Let's take planet Earth as an example. And the mass is comprised in a way that it's delimited by the surface, like our skin, for example, or here we have the circular shape of our planet. And if something wants to escape from the gravitational field of this planet, then we just have to give it enough velocity, like we did to our rocket in the beginning of our journey. And once it is fast enough, it is able to get away from the gravitational pull of this planet. But when we're talking about a supermassive black hole, or any black hole actually, we're actually talking about a supermassive, dimensionless, and this is called the singularity. So this is something so weird. It's a point of infinite density that is not even actually a point because it has no dimension. That even Albert Einstein, that developed the theory of relativity, he was not very sure that nature could possibly produce something so weird, but well, we actually observe these objects. So we have this point, dimensionless, with infinite density, and surrounding it we have this sphere, which is the event horizon. And the event horizon is the limit from which nothing can escape the black hole. So if the singularity is the hole that is kind of swallowing things around it, then the event horizon would be what makes the hole black. Because not even light, that is the fastest thing we know in the universe, can escape once it falls inside the event horizon. The fate of anything that falls inside here would be to fall towards the singularity. So when we go back to the image of our supermassive black hole, this is what we would understand a bit. So this darker region would be the delimitation of the event horizon, beyond which nothing can escape. And the singularity would be this infinitesimal point inside it that we are also actually never going to be able to see. So this is something interesting because we will never really understand what's inside the black hole since nothing can escape. Even if we would send a satellite inside, for example, well, first the satellite would be crashed in order to get inside there. But second, even if it was getting information, the information would not be able to come out of the black hole to us. So there are some parts of what's inside the black hole that will always be a mystery. But one analogy I would like to make about black holes is that sometimes they behave a bit like babies. So what do babies do, basically? Well, they cry, but that's the part that we don't want to talk about. But we can talk about their eating and sleeping. So we're going to say that these are the active and passive phases of a black hole. A black hole can be active in the moment where it's eating. So it's the moment where it's growing by capturing matter and swallowing this matter, and that's why we also see the formation of the accretion disk that I showed you. But if there is no food around it for it to eat, then it will probably be in the passive mode, where it just lies there, quiet and peaceful, and there's not much happening. In this kind of event, then we can see the light that is about to follow the black hole, and it's easier to detect them. In this case, it's much harder because it's just a dark object against a dark sky. So here we have some simulations of these two modes. This will be the active mode. Once again, you see this accretion disk, and note that even though the black hole itself doesn't shine, the matter that is orbiting it before falling inside it will be very heated, and this heated matter will emit light that we are able to observe. This is another example in which once again we have the accretion disk, and this time we have these jets that scientists still don't really know how it is formed and why it is formed, but it's something that we do observe in nature. It's just an expel of energy and matter in a very thin line. It's a bit like a jacuzzi when you have this blast of, it starts kind of as a stream and eventually it gets turbulent. Now this is an example of a passive black hole. So we see here that it is distorting the light behind it, but if it was in a different angle, for example, and it was distorting just this dark patch of the sky, we would not be able to see it. And here's another example against what would be a very bright sky, and once again we can see how the mass of the black hole is distorting the space-time around it. So, what we learned so far in our journey toward a black hole is that these objects are very massive and compact. Once something falls inside the event horizon, it will never be able to escape. And they have basically two modes. They can be active when they are eating, or they can be passive when they are sleeping. But since we don't want to fall inside the black hole and never see our families again, let's go back safely to Earth, and then we're going to think about how we can study these objects from here. So, once we get back, this is what we see in a night of clear sky, and this is the region where we just came from, where Sagittarius A star is located. But what we see here in this image is mainly stars, gas, and dust from within our galaxy, the Milky Way. And if the supermassive black hole of our galaxy is in its center, then maybe to find other supermassive black holes, we have to look for the centers of other galaxies. So this is an image if we look to a patch of the sky that is the size of our thumb, if we do like this. And then we take a long exposition with a telescope, and we see how many objects there are in our universe. So all these objects that have a cross pattern, these are actually stars from within our galaxy, but all the other objects are actually a whole galaxy. And all these galaxies will have a supermassive black hole in their center. These black holes can be either active or passive. And the ones that are active are easier for us to study because they will be shining, or well, the matter before falling inside it will be shining. So this is one example of the things that we can observe when we are looking for black holes and their interference in the dark, in the backgrounds and surroundings. So we can look to the accretion disk, which is the matter about to fall. We can look at the jets, which is this matter being ejected, and we can look to the surroundings to see how the black hole and the galaxy are evolving together. So this is an example of why it's so important to have different kinds of telescopes and different kinds of specialists in order to understand such a complex environment, such as a supermassive black hole accreting matter. So here we have many different kinds of light that are mixed together for us to understand a galaxy with a massive black hole that is capturing matter. If we want to see the hottest parts of this, the high energy of what's happening in the galaxy, we have to send a satellite to observe in X-rays, and then we will see something like this with the most heated parts associated to the black hole. So this is very useful, for example, for us to study the accretion disk. If we want to study the surroundings or the galaxy and how it is evolving with the black hole, then we're going to use ground-based telescopes to observe in the optical domain, which is more or less what we would see with our human eyes if we were looking at that galaxy. If we want to see how dust is behaving, also one kind of interaction with the surroundings, then we use an infrared telescope, such as this space telescope here. And if we want to see the jets and these jacuzzi effects, then we can look to the skies with radio antennas. And once again, when we put all these together, then we can understand everything that is happening at the same time, from the things that are colder to the things that are warmer, all the energies there together. And when we are talking about these telescopes and their importance, well, let me give you some examples of what we actually do in astronomy. So this is the biggest telescope that we have in Brazil, where I am from. And you can see that the weather is not perfect to observe the skies. So it's much better if you go, for example, to Chile, where we have this kind of telescope. And it was this telescope that actually measured the mass of the supermassive black hole in the center of our galaxy, giving the Nobel Prize in 2020. So, when we want to observe these galaxies and the interaction with the black holes, there are different scales that we could look at. We could look closely to the galaxies. For example, in this case, we see that the center of the galaxy is much brighter than the rest of it. So that's probably due to the activity of the black hole. We can go further to see the jets, for example, and then the whole galaxy becomes just this single dot. Or we can go even further away. And in this case, we have a field that is the size of actually 2 thumbs like this. And each of these points is the accretion disk of a supermassive black hole accreting matter, just in this size. So if you think that in any galaxy there is a black hole, and this black hole could be growing, and the things could be shining, well, then there is a lot for us to study about the demographics and population of these objects. And this is what I do in my research in Gaussian, and I study both the comparison of the objects that we observe in X-rays, where we want to see the high energies and the accretion disk, and also what we can observe from ground-based telescopes in the optical domain that we see with our human eyes to understand the correlations between the galaxies where we live and the way that they are actively feeding. So, I hope that you got a bit interested about this, because even though it's something that researchers do, I think that understanding a bit more of what there is in nature and in the universe is important for us all as human beings. So, we still have many mysteries to solve when we're trying to understand these very interesting objects, but some of the secrets will be always hidden inside the black holes, and I think that's what makes them even more interesting.
now same procedure. We have time for questions. Ask the question, we'll have a volunteer come and ask you, I repeat the question, and then Catherine will answer. Here goes. Let's start here.
Thank you very much for an amazing talk. I wonder why is this disc shaped as a disc? Like, to me, I have no clue about all these things. It makes sense that it's just like a sphere and everything can follow in all the angles. So why doesn't it?
Yeah, so...
Let me just repeat the question. So, the question is, why is there a disk around the black hole and not things just falling around in a haphazard fashion?
If someone asks me in a test, I should say it's the conservation of angular momentum. But what does that mean? Well, if you see many objects in our universe who have this kind of shape, for example, our solar system, all the planets are aligned, our galaxy is all kind of aligned as well. It's a way that even when things start from like a chaotic or a spherical movement, if they start to spin, then there is some laws that have to be conserved, and in the end, I mean, I can show you the calculations, but that would be a bit out of the context. But just so you know that this is something that happens when we go from a sphere to something that is collapsing, we usually have a disk. Even stars, when they are forming their initial stages, they also have a disk. It's very common.
I'll cover the first one. There we go. Oh, wait, let's start there and then move on here. Okay.
So not all black holes have the same mass, right? They're different masses.
Different masses.
And the mass is all contained within a tiny point, no matter how much mass. Do you have any?
Okay, we're going to do a back and forth here. Let me try to repeat the question. Just ask the question and then maybe we'll give you another one. Then.
Okay, well, my first question was basically that different black holes have different mass.
Okay, let's try and handle that. Do different black holes have different mass? Okay. Question answer. We'll give you one more question. Go.
And then I was wondering if that means that so all mass, regardless of how much mass, is all contained in that infinitesimally small point. And then I was going to ask.
Oh wait.
How is that possible?
Okay, wait. Let's. The second question was: is all mass contained in the singularity? If I'm right, is the question the same? So the third question, I'm going to let you ask her later. Okay. You got the question. Too.
Yes. So we have basically observed two types of black holes, and we are trying to see the one in between. We have the stellar mass black holes and the supermassive black holes. So the stellar mass ones, when we have a very massive star, the end of the life of the star, its death, will be to become a black hole. So we have, for example, the mass of 10 times the mass of the sun into this single point. And these black holes, they will be smaller in the sense that their event horizon will be smaller, but their mass will be all in this single point that is a singularity. Then we go to the supermassive ones, and we don't know actually how they were formed. We don't know if it was like the ensemble of many smaller black holes, or if they like were from the beginning of the universe and they already collapsed there. We're still studying that. And then we want to find like how do you have the small, the big, and we don't have the medium, right? So we're also looking for intermediate mass black holes. And in all these cases, they will have different masses, but in all these cases, the physics is the same, that all the mass is in this single point, singularity. And I should say, there's a bug there. There's a part like in math, we learn in school that we cannot divide by zero, right? That's not what happens inside a black hole. So that's why Einstein looked at it and was like, no, this cannot be. So there are still some things that we don't understand. How is it possible? We don't understand.
Thank you. Please. Keep your question for later.
Okay, my question is like, what happens when two black holes collide?
Sorry, black holes?
Black holes collide.
Okay, the question is, what happens when black holes collide?
That is super interesting because we had an announcement yesterday that is being bombastic in the astronomy field, which is actually about the collision of supermassive black holes, which is something that we cannot detect directly so far, but we are getting closer to the indications of it. So there is, if you look in the YouTube for like a collision of massive black holes, there is a video that's very nice that shows this example of the passive ones. So you just see how they distort light and then they start to spur, and then they become a single one. And that moment will generate gravitational waves. So if space-time is a fabric, it's as if this fabric is being distorted. And we believe that, for example, when galaxies collapse and merge, then each of the supermassive black holes in their centers will have to also collapse or merge.
There we go. Then another question.
Hi, thank you for the talk. So, when you say active and passive black holes, on life cycle of a star, how they transition from active to passive and vice versa?
Okay, so in a life cycle of a star or a black hole? Star. Yeah. How do they transition from active to passive?
Yeah, that's something that we are still trying to understand. Because when we have the stellar mass black holes, then we can follow up these events in the lifetime of a scientist. For example, it takes decades, sometimes a couple of years, for us to see the peak where the accretion is happening, and then after it kind of finished the dish, then it goes back to being passive. But in the case of the supermassive black hole, that will take like millions of years. So that's why we need the demography, the study of many different kinds and like the population of it, and try to understand, because we cannot follow a single object to see actually all this happening.
We have time for one more question. Okay, wait a minute, there you go. We'll keep your floor.
Hi, thanks for the talk. I have two questions. The first one is with the influence of the black holes on the cosmic microwave background radiation. Because you showed a lot.
Hey, we have time for one question,
Yeah.
and then we have more. We'll open up a bit later.
Yeah, okay. The second one is on the emissions that you showed. What are you referring to the Hawking radiation? Questions. Thank you.
Okay, this is too complex for me to repeat. So, did you get it?
Yes.
Can you repeat it for me, please?
So he's asking about the correlation between the black holes and the cosmic wave background. The cosmic wave background is the oldest radiation that we know in the universe. So in the universe, in the beginning, matter and radiation, they were together, and there's a moment in which the universe expands enough for it to decouple, and then it's the first time that we are able to see light. But on that moment, still the matter was not consolidated. It was kind of a big soup of things. So we did not have black holes back then. They had to form a bit later, after that moment. And the other question was about the Hawking radiation that I was talking to you also, because you were mentioning the brief story of time. So this is in fact, the Hawking radiation says that if we have a passive black hole, eventually because of some creation of matter and antimatter, it will kind of slowly evaporate. But this is proportional to the size of the black hole. So when we're talking about supermassive black hole, and we say, okay, among billions of times the mass of the sun, it will lose one antiparticle, that's not very relevant, and that's not something that we can actually observe directly. But this is relevant, for example, for the cases where people are, for example, if they wanted to make a tiny black hole on Earth, then this black hole will be so small that it will evaporate very fast because of this radiation. But that's not something that we are able to observe. It's so far just theoretical.
Perfect. I did see some more hands going up. It's so good to see that people have so many questions when our speakers are on stage. In the interest of time, I'm going to say thank you to Katerina. Big round of applause.